I don't know if we have another question. Let's see if we have another question for this one. Okay, we're done with this one. So let's look at the next question. So the next question says the threshold frequency. Again, threshold is the minimum energy required for radiation. Now they've given us cesium and potassium, which are different metals. And already when you already see different metals, I already want you to think different metals are going to have different things that are happening with them. So the frequencies might not be the same and so forth. And the types of light that's required might not be the same. So always keep that in mind. So the threshold frequencies of cesium and potassium metals are given in the table below. If they give you a table or they give you a diagram, make sure everything comes from this. We have the threshold frequency, and this is the information that we are given. The first one, 11.1, says we must define the term work function. Now I want to talk about definitions. Now in physical sciences or in chemistry, if they say define something or give the principle of or the laws of physics and stuff like that, those things don't change. A definition must remain the same. Only when they say explain something will things change. For example, if me and Bali both go outside and they say explain the temperature outside, I'm wearing a very thick jersey and a vest outside, I'm going to be like, oof, it's cold. But Bali can say, no man, there's a light breeze. And explanation depends on what you see, what you think, and what you understand. But a definition, principles, and laws are things that remain the same. This means if you open any type of textbook, it will always remain the same. So unfortunately, my darlings, you must know these definitions off by heart. And remember, most of these questions, the first question is always a definition. So if they say there are 6 to maybe 10 definitions in a problem, you already are banking up 20 marks. Please don't fail this because you are lazy to read. So let's see. Now we need to define the term work function, and that is for 2 marks. So how are we going to define this? This is 11.1, and the definition says the work function of a metal is the minimum energy needed to eject an electron from the metal surface. This must always remain the same. Let's look at the next one, 11.2. So then the next question says, which one, and they wrote that in a capital letter, please don't write more than one, which one of the 2 metals in the table has a higher work function? And what they're telling us is we need to give a reason for the answer by referring to the information in the table. So which one has a higher work function? Now I know I've got threshold there. Now remember, I just want to write you on the side. If I've got my work function, so I can say my work function is actually equal to H. Let me write it. Let me also put the H and not actually take a shortcut. It's equal to HO. So I can see that my work function and my threshold frequency work hand in hand. So a high threshold frequency means a high work function. So between the two, I can see that potassium will have a high threshold, meaning it will have a high work function because it is then directly proportional to each other. The same thing that we did in physics. So we have chosen the one and we need to give an answer by referring to the information on the graph. So for the first one, first thing you have to identify it, and it is potassium. Potassium. Please don't just write a K because on the graph they've written the whole word. And this, so you can say FO, which is threshold frequency for potassium. The threshold frequency for potassium is greater. It is greater than the threshold frequency for cesium. It is greater than cesium. So now just remember that is directly proportional to F of O. So I always love referring back to my formulas to actually help me make a decision. So let's look at another one. So it says the simplified diagrams below show two circuits. Now, when we talk about circuits, we talk about electricity and stuff like that. When we have circuits, we've got current. They've given us an A and a B. They are containing photocells. The photocell in electric A contains cesium. Remember, it is a metal. I can see there's cesium metal plate there. They are using ultraviolet light. This was introduced to us in grade 10 when we did the electromagnetic spectrum. While the photocell in B contains potassium as a metal, they are also using ultraviolet light. Remember, it has a frequency. And these are the two circuits that I am then given. Then they're telling us that ultraviolet light with the same intensity, so both for circuit A and for circuit B, they are using the same intensity and the same wavelength, right? But remember, when we look at the threshold frequency between cesium and potassium, it is different. But the frequency that they're using from the ultraviolet is the same. Keep that in mind. The wavelength is also the same. Is incident on the metal plate in each of the photocells, and the ammeter in A registers a current. So let's see what the question says. So that's information that we are given. I feel like if you are getting confused with a topic like this, wherever you read wavelength, make a lambda. Wherever you see threshold frequency, write FO. Wherever you see kinetic energy, write EK. So that when you're looking at your formula sheet, you are able to directly see what you have, what you are given, and what you are looking for. Because I know some of these terminologies can be a bit difficult, but I think as you are scanning through your paper and so forth, you can then make those nitty-gritties as you move along. So let's look at 11.3. It says, by the means of calculations, determine whether the ammeter in circuit B will also register a current. So we need to calculate. But now, remember, before I can actually calculate a current, I am given wavelength. So the first thing, I can either use a formula that uses wavelength, or I can use energy. But then remember, from the top of my head, I know that E is equal to HF. I don't really have the frequency, but I do have the wavelength. So I can then break it up to E is equal to H, and then I can say C over lambda. So this you can also get in your formula sheet. But as you see what I'm saying, you are given wavelength. The only formula that has wavelength is then this one. They want you to calculate whether the ammeter will then register a current. So let's work on that problem. See if I have space here. So we are working on 11.3. So I'm going to do it in two ways. The one thing I can say, C is equal to F lambda, because this is also another formula that uses lambda, and I know that C is a constant because that is the speed of light. If I can find my frequency, then I'm able to then say whether it can or not, whether it can then determine the current or not. So C is a constant, so I can say 3 times 10 to the exponent 8. I am looking for my F. I was given my lambda as 5.45 times 10 to the 14 hertz. If I'm looking for F, I'm going to make F the subject of the formula by dividing both sides. Just going to take a shortcut here. I'm going to have 3 times 10 to the 8 divided all by 5.45 times 10 to the 14. If you don't know how I got here, remember, I want F by itself. I divide both sides with what is irritating my F. In this case, it is this side. So 5.45 times 10 to the 14 divided by 5.45 times 10 to the 14 will then give me 1. So I'm only left with F. And on the other side, I have this. So let's put this in my calculator and see what we have. Always remember, if you are putting things with exponents on your calculator, put them in brackets. So I've got 3 times 10 to the exponent 8. I have that all over 5.45 times 10 to the exponent 14. Bring that down. Remember, then you can say SD to get in a decimal place. I'm going to say 5.50. Remember, if it's 5 or greater, then it can change the next number. In this case, 4 is less, so I'm going to leave it as 0, and that is times 10 to the negative 7. So I'm going to have, for my frequency, I'm going to have 5 times 45. Okay, yeah, now I forgot what my frequency was. 5.0 was 5.50 times 10 to the 7. 5.50 times 10 to the 7. Remember, frequency is then in hertz. But now I can already see that the frequency from the UV light is then smaller than the frequency of potassium. I can already see that that is then smaller. Or another way that we could have actually found it is the other energy one. So this one is a bit longer, but it also will get you, it should give you the same results. So if I've got E, and I'm going to say, I would say always write it out. So I've got E equals HF, and I can say E is also equal to HC over lambda, and I'm going to plug in or put in what I am then given. So I can then say, let me look for my energy to see. Remember, if you're looking at energy and you're saying E is equal to WO, you can then take the work function as the energy. Because if I write this, let me just write it out as EK max, then you can see how your energy and your work function are actually being affected. So H is your constant, which is 6.63 times 10 to the negative 34. C is the speed of light, which is 3 times 10 to the positive 8, exponent 8. I was given my lambda, which was 5.5 times 10 to the 7. Remember, the lambda was the same for both the cesium and the potassium. So let's see what I get here. So now this is the energy, and then I'm able to then conclude what is then happening. Remember to put brackets around it. I've got 6.63 times 10 to the exponent negative 34. Bring that down, multiplied by the speed of light, which is 3 times 10 to the exponent 8. Close that bracket. And here I'm going to have 5.5 times 10 to the exponent negative 7, and take that down. So this is my answer. So I'm going to 3.62, the 6 will round off the 1, times 10 to the negative 19. That is my energy. So I can say 3.6, let's say 2, times 10 to the negative 19 joules. So then let's see my work function. So if I've got my work function, let's see now I've got my energy, let's see my work function. If I say HO, and I'm going to say 6.63 times 10 to the negative 34, because I need to make a conclusion whether it can or it will not. My frequency is 5.55 times 10 to the 14. Let's see what I get, and let's see what conclusion I can draw. So this means my work function needs to be greater than my energy, and then the ammeter will not register a function or a reading. Let's see. Here I've got 6.63 times 10 to the exponent negative 34. Bring that down. Multiplied by 5.5 times 10 to the exponent 14. See, then I get a 3.65 there, 64. So I've got, here I'm going to get a 3.65. Is it 65? I can't remember. 65, yes, because the 6 will round it off. 65 times 10 to the negative 19. So already by these two, let me write my conclusion down here. So I can see that my work function is then greater than my energy, and my ammeter will not register current, because remember, this is the minimum energy that is actually then required to eject this electron. So because this one is then greater than this one, then it means that it will not have a reading on the current. Let's see another question that we can do. So we've already done this one. This one was for 3 marks. So I think regardless of which one you use, I think the examiner would have wanted you to actually choose a formula, either the speed of light or the energy one, because both of them actually have lambda. So either one of those two, maybe substituting incorrectly and getting an answer, but then you also get a mark for actually saying your statement. Remember, the question said, and will it register a current, right? So you have to give a statement to say, yes, it will, or yes, it won't. But remember how we did it? We actually looked at the work function and the energy to say, no, man, but if I've only got this for my threshold frequency, my work function is this, it means that there won't be a current, because if the minimum energy required does not fit the energy, then it means that there is no current that's going to take place. So that's how the examiner wants you to think. So let's look at 11.4. where they're telling us to calculate the maximum kinetic energy. Remember, kinetic energy is when the electrons are all excited and stuff like that. So we must calculate the maximum kinetic energy of an ejected electron in circuit A. So this is circuit A. We are talking about circuit A is cesium, and we know that it has its own threshold frequency, and this is the threshold frequency that we were given. But we were also given extra information when we got to this part to say that it has the same intensity, it also has the same wavelength. So we are still sticking to that. Now we need to calculate the maximum kinetic energy. So now let's see what we are given. Let's see what we want. 11.4, I need my maximum kinetic energy from my formula sheet. This is the formula I'm going to take. I'm going to say WO plus EK max. I am looking for kinetic energy, but I know that I can play around with this one and I can play around with my energy. Now, I don't have the energy, so I can actually calculate that. But now remember, energy, let me just write it on this side, energy is equal to HF. So it means I can replace the E by HF. So I'm going to say HF on this side, and then my work function, also you get this on your formula sheet, but you can also know it off by heart. WO is equal to HFO, threshold frequency. So I can replace this by this. So I can say HFO plus my EK, because I don't have my work function and I don't have my energy, but I am given the frequency for cesium. And this is EK max. Now I'm just going to plug in all my information, but let me just make EK the subject of the formula. So I'm going to say EK, and that is max. Take it over the equal sign. I'm going to have HF minus HFO. Remember, if something jumps the equation sign, the sign changes. So if it was a positive here, it must be a negative on this side. Now I'm going to plug in everything that I'm given. Remember, my H is a constant, which is 6.63 times 10 to the negative 34. My frequency for my cesium was given as 5.45 times 10 to the 14. Subtracted by H is a constant, which is 6.63 times 10 to the negative 34. My threshold frequency for cesium was given as 5.07 times 10 to the 14. Now, very easy, just mathematics. We're going to put this in our calculator and see what we get. Remember to always put brackets around your information. 6.63 times 10 to the exponent negative 34. That is for Planck's constant. Multiply that by 5.45 multiplied by 10 to the exponent 14. Bring that down. That is minus. Then I've got 6.63 times 10 to the exponent negative 34. That is again Planck's constant. And that is then multiplied by the threshold frequency of cesium, which is 5.07 times 10 to the exponent 14. Exponent 14, bring that down. And then this is the answer that I get. So this is going to be 5.2 because the 9 will change the 1 into a 2. Remember to always leave it in 2 decimal places. And this is times 10 to the negative 20. So my kinetic energy will be 2.52 times 10 to the negative 20. Remember, when you're talking about kinetic energy, the SI unit is then in joules. So let's see the next question. I think we have one more question to do. So number 11.5 says, how will the maximum kinetic energy of the ejected electron, remember when it's ejected, it's excited, it's floating, it's got energy and stuff. How will the maximum kinetic energy of the ejected electron, calculated in 11.4, so we must use whatever information here, how will it change if the intensity of the incident light is then increased? Now you must only choose from increase, decrease, or remains the same. But now remember, if you are looking at the maximum kinetic energy, if the intensity is increased, if you increase intensity, that just means you're going to have more and more electrons that are actually, so if you increase intensity, it just means you're going to have more and more electrons that are going to move around and stuff, but they're not going to have enough kinetic energy and so forth. So when you're increasing intensity, it'll just remain the same. It will only remain the same. Because if you change your intensity, let me just write 11.5. First things first, it will remain the same because that's what they say choose. It will remain the same. Because intensity only means more electrons will then be ejected. So this is what we have. So let's see. That was our last question. So with this one, they could have said, actually, you need to elaborate or explain. Then you would have explained and elaborated and so forth.